Hi, I'm Omkar. I'm a CosmicAI Fellow at National Radio Astronomy Observatory. In the next couple of minutes, I want to show you what radio telescopes can teach us about the very first galaxies in the universe. The galaxies that reionize the universe sit at high redshift, 6 redshifts of 6 and beyond, which are too far to study in detail. So instead, we rely on their local analogues. These are extreme starburst galaxies. They are tiny, chemically pristine, forming stars furiously, and they are leaking large amounts of ionizing photons. They look just like JWST's earliest galaxies, but they are close enough to be studied in detail in radio and other wavelengths. The open question is what's powering their intense properties, and importantly, why do the ionizing photons escape from these galaxies? The nature of feedback, which must play an important role for the escape of ionizing photons, is not yet well understood. To answer that question, we turn to radio wavelengths. Using 3 radio telescopes, we measured each galaxy's brightness across a huge range of frequencies. Then, we fit a Bayesian model to the spectrum separating the two components, thermal emission from young hot gas and non-thermal emission from supernova. Now here's the part that is interesting. At low frequencies, as you can see on the figure on the right here, we have a non-detection. However, our Bayesian model allows us to still infer useful physical information about these galaxies. It tells you the galaxy must be fainter than a certain limit. Take the case of J1032 shown in the right here. We never detect it below 3 GHz, yet folding those upper limits into the fit reveals that the spectrum turns over. It's a fingerprint of dense gas self-absorbing its own light. In order to do this, we had to add an additional error function term to the standard Bayesian likelihood to incorporate the non-detection in a meaningful way, as shown by the equation here. Across the whole sample, a consistent picture emerges. These galaxies are thermally dominant. The radio emission comes mostly from young ionized gas and possibly not supernovae. That's unusual, and it tells us the starbursts are extremely young, and a few of them, like J1032, show free absorption signature, pointing to an incredibly dense, compact star-forming clumps. So why does this matter? Well, 3 things. First, these are some of the youngest starbursts we know, dominated by massive star clusters, before possibly even supernova has kicked in. Second, that youth and density is exactly what lets ionizing photons escape. A flat radio spectrum tracks strong Lyman continuum leakage. And third, because these are local analogues of JWST's earliest galaxies, the same is likely true in the early universe. So future surveys with the next generation radio telescope should be tuned to catch this free emission. This work was supported by CosmicAI, the NSF, and Simons Foundation. Thank you.